My name is Milhouse, but some people call me by Renan Rannelli. I am based here in São Paulo, Brazil. I've been born and raised over here. I'm doing Elixir development since 2015. That's, for those of you that know Elixir, that's quite a long time. I'm also the organizer of Elixir São Paulo meetup. We try to do meetups every two months. We are a bit delayed, but you can go to meetup.com and look for ElugSP, and you know when we have more meetups. Before Elixir, I did lots of Ruby, Python, C#, and all sorts of uninteresting stuff. Today, I'm a senior Elixir engineer at Podium. Podium is a company based on Salt Lake City in Utah, United States. I'm going to talk a little bit about Podium, what it does, and just to give you guys some context. We are the lead provider of interaction management software. That thing probably doesn't mean anything to you, but I'm going to explain a bit later. We've passed the 600 employee mark on this month. We are growing very, very, very fast. We've been elected as one of the 25 next billion-dollar startups from Forbes. And just recently, we've been, for the second time, named one of Inc.'s 5,000 fastest growing privately held business in the United States. That's a feat that very few companies were able to achieve. That speaks to the velocity that we're growing. And we offer solutions for review collection and promotion. You know, Google Maps that has reviews, 5-star reviews. We collect and promote reviews for all sorts of different sources, for different verticals and everything like cars, health, insurance, restaurants, lots of different kinds of businesses. We have a solution for internal chat, kind of like Slack. We have a solution for external chat, kind of like Intercom. We offer feedback surveys, and we're going to have mobile payments soon. So we are trying to build a suite of tools to help local businesses to interact with their customers and make more money. And the good thing is we are opening an office right here in São Paulo. We have 100% of the office over here. Adam is an engineering manager from Utah. He moved down here to Brazil to build a team, and we are now a 6-person team. We're planning to grow to around 15 by the end of the year. So we're hiring. If you are interested in Elixir, if you do front-end development, if you know a good product manager, I don't think anyone over here is a product manager, but if you know a good product manager, if you know good product designers, let us know. We are actively looking for those roles. So let's get started with the meat of the talk. Like let's try to put a bit of context and talk about why concurrency matters, right? AKA the free lunch is over. I think that now in 2019, a lot of people might have seen this picture before. So if you haven't seen it, I'm going to read it real quick to you. This is a graph that shows the various properties of different processors over time. So we can see here the number in triangles, the number of transistors in a processor. And that's kind of like a straight line. And because this is a logarithm scale, every time you go up 1 unit, that means the number is 10 times bigger than the previous unit. So from here to here, the number grows tenfold. So we can see that because this is a straight line, this means that the triangles are actually growing exponentially if we had a linear scale over here. And that's the number of transistors. If we look at the single thread performance, we can see kind of like the same behavior, but over the past few years, we haven't seen these growing all that much. That's when the Moore's law started to not make sense anymore for single thread performance, but it still makes sense for transistors. Every couple of years, the number of transistors in a processor doubles, and with that, what do we gain? After 2000 and something, instead of getting more single-threaded performance, we are getting a higher number of cores, independent computing units inside the same processor. And that has a big impact in our industry and how we write software. So in summary, this picture is from an article called "The Free Lunch Is Over," and it's a very good read. And in summary, the clock speeds are not getting higher. We're getting exponentially more transistors, which means more cores, and no substantial gains in sequential performance, which means that concurrency is the next major revolution in how we write software if we want to make use of these additional compute resources. So efficiency and performance optimization will get more and not less important over time. This is the bottom line of the article, and this was written in 2005. 2005. In case you were not around in 2005, I'll give you a very quick refresh on what the world looked like in 2005. Java 5 was hot news. Can you imagine? Like everyone was, yeah, did you see that cool new technology, Java 5? That's going to be awesome. Yeah. We were using Windows XP. We would only see Windows Vista in 2005. Do you remember Windows Vista? Jesus. We didn't have AWS, we didn't have Twitter, no Netflix, no Uber, no Airbnb. Ruby on Rails would hit 1.0 in December of that year. We didn't have Justin Bieber yet. We didn't have Stack Overflow. We didn't have Stack Overflow. I don't know how people programmed at that time. Like, yeah. So the world was kind of worse, but also kind of better. So after 2005, the interest in concurrent programming has only grown. All the newer languages that came to light after that year had concurrency as a first-class concern. If you think of any language that came to light after that, Scala, Clojure, Elixir, Rust, Go, all of them take concurrency very seriously because the hardware industry is shifting, has already shifted to more cores instead of more single-threaded performance. And that has a huge impact in the way we write software. If you want to know more about this topic, there are 2 talks that I gave in the past. You can see that they're quite old because they still had hair and no beard. So if you want to know why people call me milhouse, you can look at that and that's going to be obvious. So entering the concurrent world. There is a quote that I like very much from Fred Hubbard. Fred Hubbard is one of the top Erlang developers in the world. The guy is awesome, and I really recommend that you should follow and devour any content that he produces. Everything that he writes is really good. And there's this quote that I like a lot. A simple system behaves differently from a large system, even if both provide the same functionality. So the question that we should ask is now not how to prevent complexity, but how to cope with it. The idea is that we are not going to try hiding complexity. We are going to cope with it. We are going to create tools that will allow us to reason about this complexity and make good, informed decisions. We have to cope with it. Concurrency is a complex problem, and we need to cope with it. There's no way around it. Anyone that comes to you and say, yeah, I don't need to worry about concurrency is lying. You might not know that he's lying, but he is. Many people come to me when they're trying to find an Elixir consultant. And yeah, I had this concurrency problem, and I'm going to use Elixir to solve it. And Elixir is not going to solve it. Elixir is going to help you cope with it, right? So let's talk a bit about how concurrency manifests itself in a simple web stack. Let's look at this very simple, very minimal web stack that you can very well run this on Heroku. You have the internet, you have a couple reverse proxies, you have your web servers, you have a Redis for caching and whatever, probably to run Sidekick on top. You have services, they all access the database, and they all access the cache. So this is a very simple web stack. And where do we get concurrency? Well, we get concurrency when a user clicks a link multiple times. Like you ever seen someone that tries to click multiple times in hopes that the answer will be different? You know, like, that generates concurrency for our servers. If we have multiple services doing workers at the same time, that's concurrency. If we have caching and validation, that's concurrency. We have concurrency all of the way down from the internet into the database, which is what we are going to focus on for the rest of this talk, because that's in the title, right? So yeah, one thing that most people also forget is that when you're doing deployments, and if you're doing deployments with high availability, that means you can still serve your users while you're deploying, and you should be doing this. There's no reason not to do it in 2019, but when you're doing this, you are adding new instances of your software, new instances of your system, and they have a different version of code on them. So they might make different decisions, and because they communicate through a database and communicate through a cache, you might come into very weird and nasty concurrency issues that only make sense if you have a piece of the code running in one version and a piece of the code running in another version. Those are like the most difficult ones to tackle. But fortunately, we're not going to talk about them today. Just wanted to give you guys a heads up that this definitely happens if you're doing HA deployments. We'll focus now on a single box, the relational database, and that's what we're going to focus on for the rest of this talk. Because there's lots of concurrency inside the relational database, lots of concurrency that people don't even realize it exists, right? This is where we're going to focus our attention on today. So databases are complex beasts. Some solutions in the market have more than 30 years of active development. Postgres comes from a code base that's more than 40 years old. The database had like 4 or 5 different names until this day, and some of the original code still lingers there. And people are usually surprisingly unaware of how the database is run, what properties it has, which makes sense, right? You have a piece of software that's been in active development for 30 years. You can expect a single person to know all the ins and outs of it. But we need to understand at least what are the guarantees that the software provides us so that we can make good software and we can write correct software. We are here today to bridge a little bit of that gap. So transactions. Transactions are the most powerful and valuable concept available in the database world, in my opinion at least, and probably one of the most misunderstood ones. People think they know what a transaction does and what transaction is. So today we're going to try to explore a bit of the nuance that exists in transactions. So what people say about transactions. The first thing you hear when you ask someone, well, what is a transaction in your opinion? The first thing is, yeah, the transaction is a thing that groups database operations so that they can all succeed or they all fail. This is the A in the asset, right? Availability, consistency. I don't remember the other two, but yeah. Yeah, isolation, and what's the D? Durability, yeah. Yeah. You want your database to be durable, right? One other thing that you hear is like, oh, if I use a transaction, all inconsistency problems go away. I really heard someone talk, oh yeah, transactions exist to have consistency. And not exactly. There's a lot more nuance to that. Transactions enhance performance. Yeah, sometimes. Transactions can never fail. That's completely wrong. So everything that we said are not really true. And we're going to explore that right now through an example. So from here on out, I'm going to use examples in this style to show situations that can happen in production. So over here we have a name of some operation we are going to do in our system. You can imagine this like, oh, I got a message from SQS, I got a web request, I got a worker, I got whatever. I don't care what triggered this operation, I only care that it exists. And this operation is going to execute these operations in the database, right? So, I'm going to select from orders. So I get a list of orders in memory, and they have this state. Some of them are paid, some are canceled, some are only delivered, another are paid, and the one is pending. And I want to And I do the select, then I do some stuff in the system that is not database related, and then I run an update. I do an update orders, set status paid, where the ID is 5, right? And then that goes to the database. Easy peasy, right? You guys see a problem with that? Yeah. Let's explore this. Let's look now at the situation where we get two operations running concurrently. We have an order paid and an order cancel operation, and both of them arrived at the system at the same time, and we started to execute it. One possible path of execution is we first do the select on the first operation, then we do the select on the second operation. The order into which these operations happen is only dependent on how your system does scheduling, right? If you are running this on native threads, if you're running this on processes, if you're running this on whatever, the order to which these operations happen is undefined. This is what defines concurrency. Concurrency is when two different tasks can progress at the same time. They don't necessarily progress at the same time, but they can. So we got both operations with the data selected. We are going to do this if the order status is canceled, then do a refund. We check the status, it's pending, so you shouldn't refund. You go forward, you do an update in your orders, set it to paid, it's paid, and then you put that into the database. Now, the second operation continues, tries to check whether the status is paid. It's not, so there is no refund. You set the status to cancel, and then you put that into the database. So what just happened? We got an order paid and an order cancel operations, and we ended up in a state where we have a canceled order in the database that never got refunded. From these ifs, you can kind of guess the business logic that is, okay, I have a canceled order, and I just received the payment from my payment processor, so I need to refund because the order was canceled. And the other case is the same. Well, if the status is already paid, I need to issue a refund. The problem is that you got the two messages at the same time. And because of that, we ended up with a cancel order that never got refunded. And we're talking about this today because this is the sort of thing that happens when you ignore the way that a database works. You create problems to the business. You will have, I'm pretty sure that someone here already had like the order, they charged you, they canceled your order, and the product arrived, and then you're happy. But the other way can happen as well. Like you can pay, cancel, never get a refund, the product never comes, you get mad, you need to chat with, like you go to the service, to customer service. It's a terrible experience, and we don't want to give our customers that. And that terrible experience become the genesis of that terrible experience is that there's two arrows pointing to the same place here, and we have to fix that. So how do we fix this? Transactions to the rescue, right? We forgot to put transactions. Let's just put a begin and a commit, and everything will work, right? Let's see how it goes. We do the selects. We do the check for the status. We don't issue a refund. We commit. Then we write to the database. The second operation continues. No refund because it still has in memory the status pending. You do the update. Same thing. So transactions have not really solved our issue. It's not just slapping a begin and a commit and all the consistency issues will go away. That happened because we ignored the I in asset. We ignored the isolation. We need to understand isolation in order to understand transactions. So let's talk about transaction isolation. In order to explain what transaction isolation is, we are going to do it like a bit differently. We are going to focus in different kinds of problems that you can get from databases, and the isolation level is one thing that you put in a transaction that avoids that consistency problem, right? So we have 4 different consistency problems: the dirty read, the non-repeatable read, the phantom read, and a serialization anomaly. And we have 4, we're going to discuss 4 isolation levels, because I'm using Postgres as a reference here. Depending on your database technology, you may be offered more isolation levels, you may be offered less isolation levels. Actually, Postgres doesn't have read uncommitted. It's not possible to do that because the way Postgres implements concurrency control. But generally, you will have these 4 isolation levels. And when you go from the least restrictive to the most restrictive, less problems are possible. If you have a serializable transaction, no serialization issue is supposed to happen. If it happens, it's a bug in the database. And because databases are these massive beasts of 40 years of development, usually they don't have that many. Not usually this top level, right? So let's discuss first the dirty read. I'm going to use the same example to explain what a dirty read is. That is probably something that most people are already familiar with. So once again, we select from the orders. We check if the status is canceled. It is not. We don't issue a refund. We do the update. Now the second transaction goes. It selects from the order. And because the transaction here has the read uncommitted isolation level, then it is allowed to read data that has not been committed yet, which is a terrible idea, right? That's because many databases don't even support this. They are not going to allow you to do this, even if you ask explicitly. So if you have that situation, then the status is paid, right? You issue a refund, then you update it to cancel, then you commit. And you might as well have the first transaction committing on top of it. So this is what happens when you do dirty reads. This can also happen if this transaction aborts for some reason, like a timeout, a rollback, or whatever. If you have not committed this and you have read it over here, you're completely screwed. That's a very bad system. We have an order that was canceled, refunded, and yet the status is paid. Not good. Now, what would happen if we had the read committed isolation? Actually, we already know, because that's the first example I did. The same order. We go forward, and then when we do the read, you can see it's pending. It issued a read before the commit, so it sees the pending. And we get the same situation we were discussing. Now, the next isolation level is non-repeatable read. The non-repeatable read will make, the next isolation level is the repeatable read that will make the non-repeatable read impossible, right? What is a repeatable read? A repeatable read is a higher isolation level that that's pretty much what I said already. If the transaction, what defines a repeatable read is, if a transaction reads the same data again, it will find the previously read data in place, unchanged, and available to read. This is actually a very important detail, because if you are doing the concurrency control using locks, and if you read the data and it's locked, and you can only read it after the transaction that read it committed, that's not repeatable read. That's another thing. That's concurrency control using locks. You can also solve most of the issues that I'm showing over here with the judicious use of select for update, select for delete, and that sort of techniques. Different databases will have different solutions for this, and I'm not saying that isolation is the only way to go. We can also solve stuff with locks, but to my experience and my opinion, they are much harder to manage, much harder to get right. And I would rather have this problem being solved by people that are doing 40 years of active development than me. I am not confident enough that I'll be able to do anything as closely correct as what these people can do. So, an example, a very simple example to show what a repeatable read problem is. So, if we have a select from users where the age is 20, We start a transaction 1 and we do this. And then we get back Thomas that has age 20. And meanwhile, we're doing some other stuff. Another transaction starts. It inserts into the user's table Bob that is also 20 and commits. So at this point, we have transaction 2 committed and transaction 1 is still in course. We issue the select again, and now we get both Thomas and Bob. This transaction was in place, and we issued 2 of the same reads, and we got different results. This is a non-repeatable read. This is the problem. If you have repeatable read isolation level, which is like we're using the same word for 2 different things, which is confusing, and that's not my fault, that's the literature's fault. But if you have an isolation level of repeatable read, you wouldn't get this. You would get this. You are not allowed to have your reads being changed after you did a begin. Now the phantom read. The phantom read is an anomaly that is not possible if you have serializable. The phantom read occurs when, in the course of a transaction, new rows are added or removed by another transactions to the records being read, which is kind of like the repeatable read, but it's a special case. It happens when we are doing a read based on a range and not in a key. We are not reading users that has age 20. We are reading users that have age between 10 and 30. That's a different anomaly. Right? So let's go back to the same example. We select users where age is between 10 and 30. We have Thomas, age 20. Then on transaction 2, it begins, adds Bob, commits, and then we issue the same select over a range, and then we get different results. This is a phantom read. Why is it called phantom? I have absolutely no clue. And that's what it is. It's a less common problem, and some databases don't even acknowledge an isolation level just to treat this. Postgres doesn't. Postgres goes straight up from repeatable read to serializable. Some other databases have an intermediate level. I believe that Oracle does. I think that MySQL does, but I'm not sure. I'm not experienced with those. And then there's the serializable. Serializability. I trained to do this word right, and I failed miserably. Serializability of a schedule, it's a property of a schedule, means equivalence in the outcome, the database state, and the data values. Is the complete equivalence of a schedule to a serial schedule. That is, a sequential schedule with no transaction overlap in time. It's as if every transaction waits for all the other to finish before it starts. So, serializability is the quality of a schedule of being equivalent to a serial schedule. It doesn't mean that the operations will execute at the order they were issued. It doesn't mean anything else. It means there exists at least one order into which your execution is equivalent to a schedule that has no overlap in time between transactions. This is how most people think the database operates by default. This is how, when we are learning, we read about transactions, and that's what comes to mind. Okay, so I'm putting a transaction, and then things will be consistent. Things will be serial. And that doesn't happen. And then you can ask, like, well, why doesn't the databases go through all that hassle of defining 5 different isolation levels where you can just use serializable and be good? Like, it's going to be much more correct than doing read committed. The problem is that in order to achieve this while also being performant is really hard. It's actually an open problem. No one knows how to do this in the best way possible. So the databases allow you to relax your consistency requirements in order to achieve more performance. That's what we've been doing with NoSQL for like 10 years, 15 years already. And the relational database people have been doing this since always. It's never not been a thing. So let's get to our, there's a dangling arrow. Sorry about that. Let's ignore this. But let's get to the same example and run it again. But now with serializable transactions. So we do the first read. We check whether the status is canceled. It is not, so we don't issue a refund. We do the update. Set it to paid. Now we start the second operation. It reads from the database. It's not canceled. It's not paid, so we shouldn't issue a refund, right? We do the update, and we commit. The same order of operations that happened in our dirty read example. But now, when we issue a commit in the first one, what's going to happen is that this commit will fail. This will not happen. The database will tell you, I cannot do this because another transaction ran and changed that data. You need to start again. So this is actually the very highest price we pay when we use isolation levels other than read committed. Transactions start to fail on commit. If you're using read committed, I think, at least in Postgres, I don't think a transaction can fail if you're using read committed. And read committed is the default for Postgres. So when you use a more restrictive isolation level, your application can start to fail in all sorts of different ways. Performance will take a hit in general. Even reads will be slower. Right? Another thing that I forgot to mention is that is actually very important, and I see lots of people not doing it. You need to read inside a transaction. Everything that we're talking right here, if you do the read outside a transaction, is bogus. It's not going to help you. If you do the read outside of a transaction, you are completely on your own. The database can't help you. So if you are currently only doing transactions when you write multiple stuff and not when you're reading, please stop. Because you most likely have concurrency issues in our application already, and we'll get back to that. Depending on your database technology, you can find lock contention. What I mean by that is you look at the resource usage in the database and like the memory is down, the CPU usage is down, the network usage is down, but somehow the latency on the queries are way up. And that's because you probably have a lock contention. Side effects also become very dangerous. Remember that issue refund? We don't know what this refund does. But if it does something outside the relationship between application and database, you need to roll that back as well. If the transaction fails to commit, you need to roll the side effects back. Or else you can send an email, yeah, your order was refunded. And the person goes, oh, it was not refunded. And then there it goes, customer service all again, bad experience. So, if transactions fail and need to be retried, there is a risk that on overload situations, the retries will make the problem even worse. Like the database is failing because there's too much concurrency, too much going on at the same time, and it's saying, you need to retry, you need to retry. And then your application just retries mindlessly. You can take the whole database down in that situation. Use circuit breakers for the win. Use that even in the database layer. At least have a way to do that. Application-based data replication is now twice as hard because it's a side effect, right? If you are indexing stuff on Elasticsearch, for example, you are doing your operations and in the middle of the transaction, you issue a request to index something. This is now twice as hard because the transactions are much more likely to fail. And now you might have a failed transaction with some data in Elasticsearch that doesn't exist on your primary data, and then you're back to the mess again. So how do you solve those issues? There's a whole topic of observability that I don't have time to make justice, But don't forget your database when you're building your monitoring infrastructure. Don't forget to log the queries. Don't forget to have metrics on the database execution. Understand how your database uses statistics. Understand how, at least how the basic parts of administering a database, so that when you suspect these kinds of issues are happening, you have the tool set to dig and find them. Logging and tracing help a lot, but they are quite difficult to use effectively to debug concurrency because clocks drift. The clocks, especially if you have a system that has grown, that has lots of machines, the clocks will drift, and don't rely on them when trying to figure out if you're having a race condition inside a database. Try using the database server's clock as the reference. It is very easy to forget that, and it might help a lot. So, wrapping up this whole topic, concurrency is always there when we're doing web development. The database, that is the thing that we most rely on, has lots of concurrency in it and has lots of possible race conditions if not used properly. Usually, these issues stay dormant for months after introduced and show up under situations of overload or even if your company is growing. The simplest solution that works, I'm pretty sure that everyone has heard of it, like, oh, I'm just going to do the simplest thing that can possibly work and then get over with. Yeah, that's really good when you're building a product, but if your business rely on having on data integrity, you cannot think like that when you're writing and reading from the database. You need to think about consistency, because the simplest solution that works might not work, right? As your business grows, these problems become more and more important. And as we grow, the accumulation of these dormant, consistent issues can quickly become a nightmare. You can, if you're like working in a product that has never took off for like 2 years, you might be 2 years introducing these kinds of issues. And then when you actually have business, when you actually have users, then these start to pile up. Then you have this data that's like impossible to happen. Oh, but it's not possible to have a paid but refunded offer, a refunded order. Yeah, it is if you take concurrency into account. If you have data integrity issues that are like impossible, and that's likely a concurrency bug. Proper isolation can help, but it might not be enough. The problem might be happening somewhere else, especially if you're distributed. We need to treat data as the most precious thing in the system, because it is. The data, your primary data, is the only thing you can fix. If you lost your primary data, if you screwed your primary data, you're screwed. Understanding the actual guarantees of what your software offers is fundamental to writing correct, as simple as possible, and performance system. You see that I mentioned as simple as possible. At the very beginning of the talk, I talk about how we need to cope with complexity. Because we are dealing with a complex problem, our solutions will have a degree of complexity, of course. So we should not try to hide that. We should not try to abstract that away from the developer. You will fail. If you try to do that, if you try to create, a framework that's concurrency proof, you're going to fail. The brightest minds of our industry have not been able to solve that. And even though you might be much more brilliant than I, that is very unlikely that you're brighter than the brightest that's been doing this for 40 years, right? So, understanding the guarantees is fundamental. Do your reads in the same transaction of your writes. I'm going to say it again. Do your reads in the same transaction of your writes. Pay special attention to updates. If you don't do your read inside the same transaction of your write, you are on your own. Be ready to retry transactions if you want consistency. Even though you might not have the problem today, even though you might use read committed to the end of your days, be ready to retry transactions. Don't mindlessly think that a transaction will always be successful. You, backend developer, you are the guardian of the primary data's integrity. You are the sole guardian. You are the last line of defense against the madness that is data without integrity. The free lunch is over, and yet that's not going to stop us. Thank you. Here are my contacts. If you are interested in Elixir, in React, in working in a great product in a fast-growing company, come to me. You can talk to Andrew. You can talk to Mateus. You can talk to Luis. You can talk to Adam. We'll be here to the end of the day. Thank you so much.